Hello, Honors Chemistry, and welcome to Chapter 5, Section 5.3, Chemical Formulas, which is really just a reiteration of what the stuff you guys should already know from middle school and what was really introduced in the last section, right? Where a chemical formula is composed of our symbols, right? Our element symbols, right? In addition, it's also composed of subscripts, and these subscripts give us information about whatever it's sitting next to. Yes, right? Kind of like in math, right? Where in that 2 says we have 2 hydrogens, right? The presence of no subscript there implies 1, right? Because otherwise we wouldn't have written the O if there were no implication of its presence, right? Okay. And then so for this one, right, the formula gets more complicated, but it's the same thing, right? Implied subscript of 1 for magnesium, right? Here, this is NO3. That whole of NO3 is in parentheses with a subscript of 2. What that means is we have 2 NO3s, right? And so what that means if we sort of apply it or distribute it, right, we have 2 nitrogens and we have 2 times 3, so 6 oxygens. Yes, does that make sense? Which is a total of 2 NO3s. Does that make sense? That's how we would read that. And this thing in parentheses, right, that's referred to as a polyatomic ion, which we will talk a whole lot more about later. But first, let's just make sure we can read the formulas as they're written and interpret what the numbers mean, okay? Okay. All right, next up, counting our atoms, right, just to make sure we can break this down, right? So this, again, applies to that potassium. So it says that there are 2 of those. The implication is that there's only 1 sulfur and there are 4 oxygen, yes? 2 potassium, 1 sulfur, and 4 oxygen. Here, right, this says we have 2 aluminum. Now, again, we have SO4 and we have 3 of those SO4s, right? So if we have 3 SO4, that means I have 3 and 3 of the O4. So I have 3 sulfur and I have 3 times 4, which is 12 oxygens total. Yes, does that make sense? All right, so that's just, the exact same way it works in math class. All right, and a quick note, we'll talk a lot more about ways to represent molecules when we get later into the school year, but for right now, this is just an introduction to the kinds of information we get from the different models. Your book is going to use them throughout the school year, right? So it's good to just know what it's talking about, right? So our molecular formulas, all they tell us is what is in that compound, yes? As in, you know that there's 1 carbon, 4 hydrogens, and that's all you know about methane, right? There are rules for how we write the molecular formula, right? Obviously, we write the most metallic first, right? That's what your book says, right? We write the most metallic one first to the least metallic. Later on, in later chemistry classes, right, you'll see that there's the way you write the formula gives information about the structural formula, right? But that will come later. And the structural formula not only tells you what's there, so again, we still have a C and 4 H's, but it tells you what's connected to what, right? Where these lines represent a bond, which tells you which atoms are stuck to which atoms. In CH4, it's not very complicated, right? But in a much larger molecule, that can start to be more important, right? And that's important because some compounds can have the same formula, but depending on the distribution of atoms, they will have very different reactivities, right? Like what they do will vary based on what's bonded to what, right? Then we have the ball and stick model, right? Which is where we finally get some 3-dimensional information, right? And that's one of those important things because we often forget because we work on paper, right? So we assume that we have this flat molecule where everything is 90 degrees from each other. Well, it's not, right? It's just, that's the natural way to write it on a piece of flat paper. But in real life, right, everything is 3-dimensional, right? So methane in 3 dimensions actually adopts this structure, right, which says that this bond angle, right, is not 90 degrees in real life, right? It's 109.5, right? Which then means its shape in 3 dimensions is not flat. It's not a square or diamond, whatever you want to call that, right? But it's got this unique shape, and that unique shape becomes important for how one methane can interact with another methane, or how a methane can interact with another molecule, right? The space-filling model gives us also 3-dimensional information, right? And it also gets rid of this whole concept of these sticks, right? Because sometimes these sticks can be misleading because then you think there's an actual entity there, but there's not, right? A bond is not an actual stick that forms between 2 atoms, right? And the space-filling model also gives us a little more information about how big the electron cloud of the respective atoms might be in a given molecule, right? All of which, like I said, becomes more important later on in the school year. All right, that's all we've got for this one. Thank you for listening. Be good and stay tuned for further classifications of our pure substances. All right, be good. Bye.